All right, everyone. This is our problem solving session video for October 2nd. Unfortunately, I'm doing it a bit late. I had some technical problems getting online this evening. So sorry, David. The only person who posted requests, and they were for section 11.7, problems 5 and 8. So I'm going to do those right now. Problem 5 is this find the coordinates closest to the origin question that we talked about at the end of class, I think on Thursday. So real quick, I'm just going to go ahead and list those steps again. Oops, let me move this web work out of the way. Well, x plus 2y plus 1, okay. So 11.7, problem 5. Our goal is to minimize distance from the origin to the plane, z equal x plus 2y plus 1, for example. And so this is going to be an optimization problem, but just instead of being given a very clear f of xy to minimize, there's a couple extra steps in this one. And so the way the problem's written, we know that somehow it's going to be related to distance. So we need to remember the distance formula. It's the square root from sum of differences. So x minus x0 squared plus y minus y0 squared plus z minus z0 squared. And that's going to be your distance from xyz to x0, y0, z0. And in this case, what we want is to find the distance to the origin, which is 0, 0, 0. From some point on the plane xyz. But when we do these minimization problems, we usually have a function of two variables, x and y, or another way to kind of like spot that there's an extra trick to this is to notice that up to now I haven't used the formula for the plane that's given. We use the origin part to say that we're going to 0, 0, 0, but we still need to find some way to use this equation of the plane. And so the way we're going to do that is we just consider a point on the plane to be whatever xy coordinate we have, but then z is actually going to be that formula for our plane. So we replace our z coordinate with the equation for the plane. That forces us to be considering a point that is on the plane. You can kind of think about it like if this is my plane in xy, once I pick an x and a y, I'm kind of locked into whatever z coordinate is possible. So random x, random y can be input, but then the z value has to be given by the plane equation. So the distance, plugging in 0, 0, 0 for x0, y0, z0, and plugging in xy, x plus 2y plus 1 for the point xyz, is going to be x squared plus y squared plus x plus 2y plus 1 squared. And that's your f of xy that we've learned how to work on optimization problems with. And then the only tricky part is, remember that the 1 over square root a bunch of stuff, or bunch of stuff raised to minus 1/2 power that you get from taking the derivatives of this function, they're actually not going to affect your solution. So what's going to happen is your function looks kind of messy, but when you set everything equal to 0, the part under the square root is going to cancel out. Sort of, you can think about multiplying on both sides by the square root you divide by, but the opposite side is 0, so it just goes away. Same with the negative 1/2 power. And so you should just have pretty straightforward linear functions to solve equal to 0 once you ignore that part. It's also going to be easier to simplify before you take the derivative. By simplify, I mean multiply out that thing, just so that you're not worrying about like some chain rules in there. You can group all the x squared, y squared, and xy terms together. The second request was about problem 8 in section 11.7. And so in this case, oops, didn't center that quite right. In this case, we're trying to find the maximum and minimum values of a function on a rectangular region. And it says do this by looking at level curves and gradients, but, and I misspells gradients, but using gradients just means we're solving those grad f type equations, and level curves just means you're thinking about when functions are equal to fixed values. So this is not as complicated as it kind of sounds at first listen.